How's the formula sheet coming along? Get it for me by tomorrow. I want to look at it before I give you guys the exam. How's everyone feeling about the exam? Shaking their heads no. Brianna said she's feeling great about the exam, so obviously I need to make it more difficult. Travis actually accidentally picked an exam question to go over today's class, so this question is no longer on the exam. So he saved you guys on a 1 in a however many question chance. What is it? It's probably like 360 questions, so it's a 1 in 360 chance that he managed to actually pick the one question on the exam. Yep. So, does anyone have any questions about anything? If you guys have any particular problems you want to go over, I recommend you send them to me now, because then I can just kind of quickly add them to the PowerPoint. But obviously we don't need to do that. I won't add it right away. Just send it to me. Otherwise, I've got a handful of questions here. For questions that could potentially be on your exam, those types of questions anyways. Basically, just as a recap, your exam is going to be chapters 4, 5, and 6. Not every section from those chapters is going to be covered. Only the the non-starred sections are going to be put on your exams. So if you guys look at your textbooks, you'll see sometimes you'll see a star next to the whatever the symbol is. So those types of questions likely won't be on the exam. Here, let me see real quick. If I go over to the syllabus. So, yeah, stuff basically just whatever's on the syllabus is what's likely to be on the exam. All right, anything from chapters 4, 5, and 6. Chapter 9 is not on the exam, so please do not be studying deflections at this point. All right, so we'll go ahead and just jump straight into this problem here. This was suggested by Travis. So we're given that the bending moment in the reinforced concrete beam is 100 kip feet, and the modulus of elasticity for concrete is around 3,625 KSI and 29,000 KSI for steel. And we're just asked to determine the stress in the steel and the maximum stress in the concrete. Let me increase the text here a little bit. I'll give you guys a second just to write out those problems. But this is basically textbook problem 451 in your beer textbooks. Not all of the problems in this PowerPoint are from your textbook. I just find some of them online from other textbooks. I take them from the COT class, for example. It's and we're just modifying whatever. All right. So one thing that you'll notice about this concrete problem, unlike every other problem that we have covered so far for concrete, is what? It's got the little T shape on the top. So whenever you see anything like this, there are two possibilities for which the neutral axis can occur. The first is either going to be within the flange, and then the second is going to be directly in the web. So because of that, you usually make an assumption that first the neutral axis is going to be located in the flange. And obviously, if you find out, for example, we do all of our calculations assuming that our depth to neutral axis is C. We make an assumption that everything is within that dashed line above first. And obviously, if we find out that that depth to neutral axis C is within that flange, great. That's our section. But if we get that C is greater than 4 inches, then technically, by finding C to be down here, that C is not exactly correct, but it does indicate that it goes below that flange. So because of that, you need to have an entirely additional section dedicated to this full flange, and then your C would really be solved from the bottom of that flange there, because we know that the bottom of the flange is at a fixed point 4 inches below. Does that make sense to everyone? I'll go a little bit into it. So hopefully it'll be located below. So first step with solving any single composite problem is we want to determine the modular ratio. For concrete problems, it's always going to be ES over EC. So it's going to be the 29 over 3.625, which this ends up equaling 8. 8 exactly, nice. All right, now the next step with any composite problem is transforming one material to another. In this case, we are referencing steel to concrete. So we're going to be transforming that steel to an equivalent region of concrete that would yield the same stiffness. So what we need to do is take all of the steel here, and then we just multiply it by N. So our NAS term is just going to equal the 8 from the N multiplied by pi over 4 times a 1 inch diameter squared. Which gives us around 2 pi inches squared, or 6.283 inches squared. Now that we have our transformed section, we need to now just develop a table, all right, to determine all of the properties for the steel and the concrete. So what we're going to have is a component table. We're going to have an A. We're going to have a Y bar and an AY bar. And in this case, because we don't know where the neutral axis is, there are two things that we ultimately need to do. The first would be to assume that all of the compression is occurring within the flange. All right, so we're going to have the flange term. We'll have a potential web term because there may be some compression in the web, but we'll ignore the web right now. So I'm just going to write the web, and then I'm just going to do all of the calculations. If we need the web, I'll actually do them in red. So that's a question mark. We don't know if we need that yet. And then we need the bars. All right. So the area of compression in the flange is equal to what? What is the height that this block is equal to? For concrete, we always take it generally from the side opposite of rebar. So wherever basically the concrete compression is. So this depth of compression is just going to be some unknown variable. We can call it C. All right, so the area that's under compression is just going to equal 24 inches times C. Now, Y bar is just going to be the point with respect to a known location. For this problem, I would take our known coordinate point to be directly at the top flange, just so that way we're not having to do like 20 minus C over 2. We could just do C over 2. And then a Y bar is just going to be the multiplication. So it's going to end up being 12C squared. Now again, we're not assuming any compression in the web, so just ignore that entirely. For the bars now, we need the A, Y bar, and AY bar. So the area is that 2 pi that we had previously computed. Its Y bar is the location from the top of the cross-section, which is going to be 20 inches minus 2.5 inches, because the 2.5 is the location to the center of the bars. So 20 minus 2.5 is 17.5 inches, which means that 2 pi times 17.5 gives us 35 pi. Now, we have to add the a's and we have to add the AY bars. So what we end up with is 2 pi plus 24c is equal to, or not equal to, and then we end up with 12c squared plus 35 pi. Now we should know from the equation y bar is equal to the sum of AY bars over the sum of the areas. With the location that we're taking with respect to, this actually gets very simplified very quickly because our base value is with respect to C. So by taking it at the top, we can just say that our y bar value is the location of the neutral axis C, and that is equal to 12c squared plus 35 pi, all divided by 2 pi plus 24c. Now, you can rework this to end up with a quadratic equation. I am too lazy for that, so I will be using my Casio calculator just to figure out all of that. 35 pi, 2 pi plus, oh, whoops, I did a oopsie, crud. 24 x. And what I end up with is a neutral axis depth of around C is equal to 2.78 inches. If anybody wants to take a shot at trying to solve that using the quadratic equation, I recommend you do so. But, so feel free to fact check me on that value. But assuming that that's correct, what does that tell us? Is our assumption about full compression within that flange being, is it correct? Yeah. So, because of that, there's no compression in the web, which means that the web, entirely useless to the calculations. Don't get tricked by it. If we had gotten that C was greater than 4 inches, which is the thickness of the web here, then our flange would have been the 24 times 4, and then the web would have been the terms as a function of C, and then we would have had to find what C was with respect to the bottom flange, and then that would have been able to help us in determining the neutral axis location from there. So we would have gotten an entirely different equation at that point. Make sense? Awesome. So, with this, let's just continue. What we now have is a dy term in terms of inches, and a dy squared term, which is going to yield inches to the fourth, and an ix term in terms of inches to the fourth. Where is the center of the compression block with respect to the neutral axis? It is just going to be C over 2, right? So 2.78 divided by 2. This should just be 1.39 inches. So basically that is just this height here, which we should all hopefully agree is C divided by 2. And then for the bar, it's just going to be the 20 inches minus 2.5. That would give us this dimension here, which was the 17.5 inches, which means that this distance here would be the 17.5 minus C divided by 2. So it's 17.5 minus the neutral axis location, which is 14.72 inches. All right, square that, multiply it by 2 pi, and we get an area of a dy squared of 1362.1. And then for this one, for the flange, I get, is that right? A times 24 times c times alpha x squared. Oh wait. Hold on, sorry. 24 alpha x times alpha x divided by 2 squared. Right, so then this should be 128.43. Somebody fact check me on that. I just want to make sure that I'm right. Would have been, yeah, I think it's that. Okay. Yeah. And then for the IX terms, for the bars, it's going to be like pi over 64 times the diameter squared, which, guess what? It's going to be a very small number. Just assume it's approximately 0. It's going to have minimal impact on the calculation, on the final results. All right. But then we end up with the BH cubed over 12. So this IX term is just going to end up being 24c cubed divided by 12. So 24 alpha x to the power of 3. Divide that by 12, which should yield 42.81. Whoops, that is the wrong side. All right, so we should get that IX total is equal to 1533.34 inches to the fourth. Are there any questions about that so far? No? All right. Now all we're left with is just determining the stress in the steel and the stress in the concrete. Because our entire second moment area of inertia is dependent on concrete, we can find the stress in the concrete. Sigma C is equal to my over I. The bending moment is 100 kip feet. Convert that to inches by multiplying it by 12 inches per foot. The Y bar is going to be located a distance c above the neutral axis, which should be 2.78 inches. And then our I is that 1533.34 inches to the fourth. And we get that the compressive stress is 2.18 KSI in compression. And that is the maximum stress in the concrete. Now for the steel, it's a similar equation, but now we need N to transform the concrete back into steel. N is equal to NMY over I. So we have 8 times the 100 kip feet, multiply it by 12 inches per foot. Its Y bar is going to be at 14.72 inches. Because that's the location of the rebar from the neutral axis, divided by the 1533.34. And this should yield roughly 92.16 KSI in tension. I'm an idiot. I forgot that there are 4 bars in here. There's 4 pieces of rebar. I was wondering, because the stress in the steel was like very large. Yeah, like 90 something KSI. So you would need like a grade 90 bar. So let me just do this really quickly, just to update all of these parameters. So that's 25.132 inches squared. That yields this. So what is that, 8 pi? So that might actually change the answer here. Eight pi. $24. Let's see. 8 pi, and then 8 times 17.5 is 140 pi. So then that gets removed, that gets removed. 140 pi, 8 pi. So then we gotta resolve this. Alpha x, alpha equals 12, alpha x squared plus 140, alpha pi, shift pi, divided by h. I messed up, whoops. And what we end up with is, yeah, a problem. We end up with a depth of neutral axis of 5.10 inches. So there is a problem. So everything that we did was assuming 1 bar, all right? We've got a big problem. All right? So, with that in mind, we now need to see what we need to do. So we got to reevaluate everything. Let me erase all of this. Sorry about that. So that's less than 4, so no good. So let's head back over to our red really quickly that I had written previously. All right, that is going to end up being 24 times the 4 inches, so the full width of the flange plus the full depth of the flange, so 24 times 4 is going to be 96. This is going to end up being 4 inches plus C over 2, right? And this is all basically now treating it as this. So that is the full compression block, and this is that. And I want to basically solve everything where this is C, the location of the neutral axis. So the center of this is just going to be 4 plus C divided by 2 from the top flange. So 96 times 4 is 384, plus 96 divided by 2 is 48C. The web is going to be, nope, sorry. I'm like trying to rush through this and I should not be. The center of this from the top is 2 inches. So please ignore that. 2 inches, 96 times 2 is 192. The web is going to have a neutral axis of 4 plus C over 2. The area is going to be 12C. And then AY bar is going to be 48C plus 6C squared. And then those bars are basically the same location from the top flange. So that cancels out. So this ends up being 8 pi plus 96 plus 12c. And then this becomes 192 plus 140 pi plus 48c plus 6c squared. And then with this in mind, our y bar, which is the depth of the neutral axis, is not c anymore. It's technically 4 plus c, because this is our full y bar now. So it's 4 plus c. So 4 plus c is then equal to 192 plus 140 pi plus 48c plus 6c squared divided by 8 pi plus 96 plus 12c. And then that is the quadratic equation that we need to solve. And for this, I get that C is equal to 1.15 inches. Now, that is 1.15 inches below the bottom of the flange, which means from the top of the flange, y bar is equal to 5.15 inches from the top of the flange. Does that make sense?
Can you draw that out?
Yes. So 4 inches, this y bar is equal to the 5.15 inches, and then that value C that we had calculated is this height here, which is the 1.15 inches. Does that make sense? So you can see that there's some partial compression in the web. Don't make the same mistake I did with the rebars. Make sure you multiply it by the actual number of bars. All right. And yeah, so I'm not going to repeat the process of doing the my over I. It's the same exact process at that point. The only thing with is just finding the second moment area of inertia. I could do that real quick. So now we have to do dy in terms of inches, a dy squared in terms of inches to the fourth, and then ix in terms of inches to the fourth. All right, so for the flange, it's just going to be 2 inches. So 5.15 minus 2, that would make this 3.15 inches away. For the web, it's just going to be C divided by 2, so that's the 1.15 divided by 2, which gives us the 0.58 inches. That's this dimension here. This one, right there. And then for the bars, it's just going to be whatever this dimension is. So that would be 20 minus 5.15 minus 2.5, which gives us 12.35. Multiply a times dy squared, 96, times 3.15 squared. Oops. This gives us 952.56. 12 times 1.15 times 0.58 squared gives us 4.64, and then 8 pi times 12.35 squared gives us 3833.31. So yeah, it's a big difference in the second moment area of inertias. The Ix of each term is just going to be 12 times 4 cubed divided by 12, so 4 cubed gives us 64 here. For the web, it's going to be, 128, my bad. Because 24-inch width, not 12-inch. This one is going to be the 12-inch width, so it's going to be 12c cubed divided by 12, so it's going to be 1.15 cubed. So this is around 1.52. And then for the bars, just assume it's approximately 0. And then your Ix total is just going to be the sum of everything. So we should get around 4,793.31. And that is the corrected second moment area of inertia. Hopefully everyone can figure out the stress part from there. Because then it's just as simple as just figuring out what the y bar is of the, what the y is in your equation. We know what m is, we know what I is. Y is just the positional coordinate of compression from the neutral axis, which would be 5.15. And then for the steel, you would use the 12.35. All right. That one took about 30 minutes with the problem, so I guess I'm kind of glad I took that one off because even I made a mistake on it. I got tricked by it. All right. So problem 2 now. I'm going to skip that one. I'm kidding, Brianna. That would have been mean. All right, so now for this one, we're basically given a steel pipe and aluminum pipe, and they're basically bonded together. And this is basically just going to be a composite beam that is subjected to some type of bending stress. So what we're basically asked to do is just find the maximum stress in both the aluminum and the steel. All right, so the first step, again, with any composite problem, is we want to determine the modular ratio between two materials. So in this case, I want to transform, let's see, I think I want to transform the steel to aluminum just because the steel is going to be stronger. So by transforming the steel to aluminum, it's going to be equal to the 200 gigapascals divided by 70. Which gives us 2.86. Now, the nice thing about this problem, we don't need to find the neutral axis. Why? It's symmetric. We know where the neutral axis is. So we know that the total Ix term is just going to be the summation of the individual Ix's. All right? So let's get the Ix for the aluminum. And that is basically just going to equal pi over 4. I should note that the I for a circle is equal to pi over 4 r to the 4th. All right. So pi over 4. For the aluminum is kind of like a pipe on the outside, so we got to do outside minus inside. So that's going to be 10 plus 6 plus 3, that's 19 to the 4th, minus 16 to the 4th. This is going to yield massive numbers. 50,882 millimeters to the 4th. And then Ix for the steel is just going to be pi over 4 times 16 to the 4th minus 10 to the 4th. Reason being is because all of this space here, I know it's a little hard to see, is it's all void space. All right, so that interior section of this entire cross section is just void. All right. Now, This is the second moment area of inertia of steel. But what's our reference material? Aluminum. So we got to multiply this entire thing by 2.86. So that way we get it in terms of equivalent aluminum. So pi over 4 times 16 to the 4th minus 10 to the 4th times 200 divided by 70. And I get that this is around 124,622.5 millimeters to the 4th. Now, IX total in terms of aluminum equivalent, so the total second moment area of inertia for the aluminum equivalent would just be the summation of the two, which we get 175,504.5 millimeters to the 4th. Now we're given that the bending moment is 500 Newton meters. So we can just now kind of plug into the equation. Sigma is equal to my over I. For steel, I'll actually do aluminum first. The moment of 500 Newton meters, this is equivalent to about 500,000 Newton millimeters. The location of the extreme tensile compressive stress for the aluminum is going to be exactly 19 millimeters away from the neutral axis, because that's it's symmetric, so it's just going to be that 38 millimeter diameter divided by 2. And then we divide that by the 175,504.5 millimeters to the 4th. And what we end up with is 54.13 newtons per millimeters squared, which is the same as saying megapascals. What about the steel now? For the steel, it's just the same thing, but you got to multiply it by n, and you need to change the y-coordinate to represent the max extreme fiber for the steel, which in this case is going to be 16 millimeters. So we have 2.86 times 500,000 Newton millimeters times 16 millimeters divided by that 175,504.5 millimeters to the 4th. And I get a stress of around 130.37 newtons per millimeters squared, or megapascals. And that's that problem. Any questions about that? All right, those were the 2 recommended problems that I had received. Does anyone else have any other questions that they may want to work on? Otherwise, I can just continue working on the sample problems that I had just grabbed from here.
Would you be posting these questions on?
Yeah, I'll post both the blank slides, so that way if you guys want to give it a shot at it yourselves. Just because, we've got half an hour left, so I'm not certain we can get through all of the questions. But at least if we could get through another 2 questions, then I feel comfortable enough giving you guys 4 questions for the exam. Because even I made a mistake on a question 1 and I was able to figure it out too much. issues. All right. Next question. A nice calculus question. All right. So with this, we are asked with determining the equations for shear and bending and also finding the maximum absolute value for the bending moment in the beam. All right. One thing you guys will notice is you are given a distributed load in terms of a cosine function, which makes it nice and fun. So, some things that we need to remember. What is the derivative or antiderivative of cosine? Yep, so hopefully you guys are aware of that. I know I always struggled with that, but I've gotten kind of used to it by now. All right, so the first thing that we need to know is how do we determine what the shear force is ultimately going to be? To simplify things, we can kind of just set our x-coordinate equal to this, because that is really how this diagram is kind of defined. So our x-coordinate is assumed to go from A to B. That should really be defined in the problem. It doesn't, though. All right, so that helps us. That means that when we cut a section and we analyze, let me draw it out a little better. We've got our function w is equal to w naught cosine of pi x over 2L times x. Our shear force we'll assume is that, and our bending moment we'll assume is that. This is going to be m of x and v of x. All right. Now, there are a few ways you could do this. Obviously, we're going to need to do some variation of integration. So we should note, if you guys look back previously in your slides, I believe the relationship for how shear force is defined when you're given a distributed load as a function is defined as the variation in shear over some distance dx is just equal to, well, let me rephrase it. If we do the sum of the forces in the y direction and we set that equal to 0, we are going to be left with negative v of x minus w naught cosine pi x over 2L, which means our shear force is equal to negative w naught cosine of pi x divided by 2L times whatever that, it's not exactly this. Let me rephrase this. It's the area under that curve. Does that make sense? We need the total area under the curve, so that was kind of a wrong thing to say. So Vx is just going to equal negative w naught times the integral of cosine of pi x over 2L dx. All right. What is this equal to? Who here remembers their cosine integrations?
Is it w naught 2L over pi x times sine, and then it's positive?
The x doesn't get factored out, just the coefficient.
Oh, yeah, yes.
Yes, so you're right. So that integration ends up equaling, you said w naught 2L divided by pi sine of pi x over 2L. Now this is an indefinite integral. So similar to what you've seen with chapter 9, you have the horrendous nightmare of plus C1. All right, but there's a nice thing about this, all right? remember when we were introducing the relationship between bending moment and shear force? What was the bending? How do we determine the bending moment? What was that equal to?
The integral of the shear force.
Exactly. So we could determine m of x through integrating the shear force diagram. Oops. All right. So the integral of w naught 2L over pi, well, that whole thing can just get kind of dragged out, times the sine of pi x over 2L plus C1, and that whole thing gets integrated by dx. All right. Now, what does this yield us? And don't worry, I know that C1 is probably freaking some of you out right now. But again, similar to when we were dealing with the deflections and those coefficients were dependent on the boundary conditions, this too is going to be dependent on the boundary conditions. Instead of it being compatibility with deformations, it's compatibility with forces, though. Does that make sense? You guys will kind of see where we're getting at. All right? So, bending moment diagram. What do we end up getting for that bending moment? So we've got, I'll just rewrite it here. V of x is equal to W naught 2L. So I'm going to say 2W naught L over pi times sine of pi x over 2L plus C1. And then what is m of x equal to?
W naught 4L squared over pi squared cosine of pi x over 2L plus C1x plus C2.
Exactly. All right. Now, we have two coefficients, but fortunately we have two equations right now to determine what those coefficients are going to need to be. All right. Now let's look at our problem. Where do we know the shear force is going to equal 0? If we were to draw this out in some type of diagram, where would the shear force have to equal 0? Where?
At B?
Not at B, at A. B, there would be a shear force, and that shear force would actually equal the vertical reaction force, right? But at A, there's no resistance at A. And what you'll actually find is that both the shear force and the bending moment are 0 at point A because it's a free end. It's not resisting anything. So we need V at x equals 0. And we know that that is just going to equal 2W naught L over pi sine of 0 plus C1. And we know that that shear force has to equal 0 at that location. All right? Sine of 0, guess what, is 0, which means that we end up with our first coefficient equal to 0. Now the bending, yes?
Two questions. Should it be negative cosine or is it positive?
It is negative cosine, but if you look at our equilibrium equation, our shear force was equal to negative cosine already, so the negatives cancel out.
Okay.
So,
Another question.
yeah.
Should there be like an AY component, like a force?
No, the reason being is because it's a free end at A and it's fixed at B. So if there was a vertical reaction force at A, it would be statically indeterminate.
I see.
Yep. All right. Any other questions? Awesome. All right. Continuing, we know that the bending moment at the free end has to equal 0 also. So 4W naught L squared over pi squared cosine of pi x over 2L, but x is equal to 0, plus C1 times, C1 is just 0, x is just going to be 0, so plus C2, which gives us, well, this has to equal 0. So what we get is that C2 is going to equal negative 4 W naught L squared over pi squared, because the cosine of 0 is just 1. So for our v of x equation, we can just replace C1 and just get rid of that. So I will just cross that out, cross this out, and then I'm going to replace this with minus 4 W naught. Yeah, I'll just rewrite it. So we get 4 W naught L squared over pi squared times cosine of pi x over 2L minus 1. And that is the bending moment equation. All right. Now, what did the question ask us? That was the part A equation. Now we need part B. The maximum absolute value of the bending moment in the beam. Well, what's going to be the maximum location at which max bending can occur? It's whenever cosine is going to, that cosine term is just going to be 0, right? So we need to know when the cosine term is just going to equal 0. So basically M max, whoops, the absolute value of that is just going to be 4 W naught L squared over pi squared, because cosine of pi x over 2L is going to have to equal 0. Now we can figure out where that is. Cosine of pi x over 2L is equal to 0. So where would that be? What is it? Cosine. I'm actually curious. Cosine. That would just be at x is equal to, I don't even know. Whatever. Either way, that would be the maximum bending moment that the beam would undergo. Any questions about this problem? No? All right. Now we've got a few other options for questions. This one is calculating the maximum shear stress. I think that one's kind of a simple one. I think I want to do this one next. That's just a composite that's not concrete. And then this one is just drawing the shear and moment diagrams. Yeah, so I think this one is the one that I want to do. All right, so we're asked here to determine the lightest W shape for the beam shown. We're supposed to solve it two different ways. The first way is just assuming that the maximum stress is limited to the yield stress. And then the second option is assuming that full yielding of the cross-section occurs. Now, what is the difference between both of these? If we limit the maximum stress within the beam to be limited to the yield stress, how does that stress distribution look? Say that again? Yeah, so don't say it. I'm going to let everyone else figure it out. How would the stress distribution look? Think back to your homeworks. I gave you guys a certain problem with this that I think only like one student actually answered fully, because it was the bonus question. Well, where's the maximum stress occur in a beam? Let me ask that. Yeah, sure. Where would the maximum stress occur in the beam, assuming linear elasticity?
Would be at the point that you're pressing down.
Not quite. Looking at it from like a W-shaped cross-section. All right, so we know that it's a W shape. I'll draw like a quick sketch here. If this is the cross-section here, oops, that's the neutral axis.
Oh,
Where's the maximum stress occur?
the extreme fibers.
At the extreme fibers, all right? So it occurs at y bar, all right? What would the stress equation be for that?
M y bar over I.
Or simply put, m over s. All right, so let's do that real quick. First, we need to know what the maximum bending stress in the beam would be. All right, so we can draw out a quick moment diagram, which would require us to find the vertical reactions first. All right, so this would be 45 times 7 divided by 2. That would be 157.5 from the distributed load plus 110 times 3 over 7. I get a vertical reaction force of 204.64 kilonewtons. Somebody fact check me on that. And then this one would be 220.36 kilonewtons. Somebody please confirm that reaction. I really want to make sure that it's right. I do not want the same issue as earlier today.
Is that applied moment W into 45 newton meters? I just can't.
Kilonewtons per meter. That's the distributed load.
Oh, there's a distributed. Oh, okay.
Yeah, that's what it's a little hard to see. That's a distributed load. It's just represented by a single line.
Gotcha. I thought that was applied moment.
Yeah, sorry. Reactions, everyone get them?
Yeah.
They match?
Yeah.
Awesome. Now, when you draw out the shear force diagram, it should look like that. All right. You follow up, tip to tail. So you go up 204.64. you add up to the next point, so the next discrepancy is at the point load. So you get 204.64 minus 45 times 7 minus 3 is going to be 4 meters, which gives you 24.64. All right, from there, you subtract the point load, so you drop down 110, which brings you to negative 85.36. Then you subtract 45 times 3, and that brings you to 220.36, which should align with your vertical reaction force on the opposite end. All right. Questions about this? No? How do we determine the max bending moment now?
Find the area under either like the positive side up until the point load.
Yeah, so we know that the maximum bending moment in this case is going to occur where the point load is located, primarily because the shear force diagram crosses 0 at that location. And wherever the shear force crosses 0 is a point of maximum bending. In this case, there's only one, which occurs directly at the point load. So what we end up with is just having to take the area underneath that parallelogram. You can either do it by splitting it up as a rectangle and a triangle. My preferred method is just adding the 2 points, dividing it by 2, and then multiplying it by the width. So either way, you should end up with a maximum bending moment of 458.56 kilonewton meters. All right, so we end up with a peak here of 458.56. Keeping in mind that V of x is in kilonewtons and that M of x is in kilonewton meters. All right. How does the bending moment diagram look? Any takers? No, you're trying too hard today. Somebody. You're staring at me, Will. You know it? Take a guess.
When the curve up rapidly and then slow down until it reaches maximum, it's going to speed up and until it gets to 0.
Exactly. How do you know the concavity of the curve, though?
Because the shear starts high and decreases and slowly decreases.
Exactly. So we end up with a concavity that looks kind of like this. And then it closes out at 0. Our maximum bending is roughly around there. It's not a perfect sketch, but it's enough to tell that it's a quadratic distribution. Thanks, Will. All right. So now, assuming full elasticity, we could just plug in M over S, but we don't have S. It's A992 steel, so the yield stress of the material is 50 KSI. So we could determine a minimum S requirement, which we would just need to plug in 458.56 kilonewton meters. My bonehead just realized that I gave you guys the stresses in terms of KSI, and the entire problem is in metric units. So I will fix that. Let me look up really quickly. What is the conversion rate. KSI, not chi, KSI to MPA. So it's around 400. So around 400 megapascals. Oops. Oh. Why did I put? Oh, yeah, exam 2 review. So this is around 400 megapascals. That would give us let's see, 458 kilonewton meters. It's around 45856.0000 Newton millimeters. Divided by 400 newtons per millimeters squared. So S min would just equal, okay, that seems reasonable. 1146400 cubic meters. Or cubic millimeters. All right, and then you would just go to a steel table, I think. This here actually has some decent values. Okay, yeah, these sizes are reasonable then. Yeah. I'm not even gonna decide a shape because it's good enough for what we needed it for. All right, now, plastic section modulus is what we need to determine the required section shape considering full yielding. All right. How does this change anything? What do you guys think? Well, simply put, Z-min would just be the same as S-min, which, when you guys come back, like when you guys leave the class, you guys will, I recommend you guys take a look here. You'll just find that the plastic section moduli for standard steel shapes is generally larger. So because of that, you would use the same section modulus that you would need and just look at the Z table, and you would actually find that you can use a smaller size shape. Does that make sense? So you would just replace the Z with the S, and then when you go to a design table like this, you can actually just look up directly. So for this, for example, let's see. So this required section modulus using S, we could go with something like a W460 by 74. And I don't have plastic section moduli on here. Here, let's see. D by 74. Yeah, you can see. So the plastic section modulus is actually somewhat larger. So because of that, you can actually go with a shape with a plastic section modulus to get closer down to the value, which would in turn allow you to be able to more optimally design certain steel structures, if that makes sense. Yeah, I thought this table had the plastic section modulus. I was really hoping it did, but it does not, unfortunately. All right. So this would just end up with a shape. All right. There's about 3 minutes left. Either you guys can stick around and we can work on problems during office hours. Otherwise, if you guys want to leave, you can feel free to do so. I'm not going to hold you guys captive here. Just remember your exam is this upcoming Wednesday. Please send me your formula sheets and yeah, so. Yeah.
For the formula sheets, can we use like small diagrams, not example problems?
Yeah.
Okay.
Yeah, I'm giving you guys a little bit of freedom just because, like, you know, I'm figuring you guys will be comfortable using the formula sheets and putting a lot of stuff on there. It gives me an excuse to give you guys more difficult problems. Any other questions? Does anyone want to continue working on other problems? I guess give this problem a shot, just real quick. Try and see if you can't draw the shear and moment diagrams for this. I know it's a little bit of a sketchy image, no pun intended, but
What number is at the end there? At the,
what?
what are the two?
Oh, those are both
forces?
300 Newton
Okay.
forces. I know, the image sucks. This I got from a textbook solutions manual from like 1964. So. So how many problems is that? 4? Okay, so then yeah. 4 problems for your exam should be good. Because even with the mistake I made on the first one, there was still plenty of time. So I just proved it. The exam is fair. I don't want anyone to panic though, so please don't be panicking for this exam, alright? I should also note the image is so poorly drawn. A should be a pin. That's a pin.
Oh, I thought that was a.
That's why there's A, Y, and AX here.
Oh.
All right, so please keep in mind that's a pin. All right, it is, otherwise, because I saw on your image what you were sketching, because if it wasn't a pin, it's statically indeterminate because of the cable.
I was trying to figure it out.
Yeah, it's a pin. Let me actually just sketch that in now. While you guys are doing that, let me see if I can upload the homework solutions. Where's Kevin back? Oh, there you are. Sorry. I'm like losing my mind. You did it? And then Brianna, you submitted online, right? Alright, cool. And the solutions have been uploaded, so everyone should hopefully now have access. Did you guys figure out the diagrams yet? Let's see. figured out? No? What?
I don't know if the diagram should.
I got the shear and axial diagrams. I'm actually running into a little bit of challenge with the moment diagrams. So, what'd you guys get for the all right, reaction forces? What's the force in the cable? What is it?
Oh, and you're asking for the number?
For the force in the cable, yeah.
2,400.
2400. I got 3200. How'd you get 2400?
From the moment equation, moment at A, negative 300 times 0.2 meters plus negative 300 times 0.4 meters plus.
Should be 0.6 meters. Because that load is 600 millimeters, or not 600. Yeah, 600 millimeters away from A, not 400. Yep. So that force should be 3,200 newtons, giving the cable 3,200 newtons in tension. From there, you should do some of the forces in X. You would find that AX is 3,200 newtons moving to the right. And then AY should be 600 newtons moving vertically upwards. So you should get that. Everyone got that? Awesome. Now, for the shear and axial force diagrams, they should look somewhat like this. I'm still trying to fully figure out the moment diagram. Oh yes. I think that's where I went wrong. Okay, yeah. For the moment diagram. All right, so for the shear force diagram, what you have to do, I set a reference fiber along the bottom, and then I assigned a reference fiber on the right-hand side here. All right? You don't have to do that. I wanted to add the little bit here to the shear and moment diagram. If you were to look up the textbook solution and manage to find this somehow, it actually won't give you the diagram for this part. It'll consider it as an applied moment here, which then you need to consider in the moment diagram. All right? With this, I like to have this little contribution provided, just for a little bit of extra clarity. So, following tip to tail, you find 600 newtons, goes vertically upwards. There's no point load applied at all until you reach this 300 Newton force. Drop down 300 newtons, and you're left with a shear force of 300 newtons all the way up until point B when you drop down to 300 newtons. Now, what about this part DF here? Technically, the shear force is going in the X direction, so it actually has no direct impact on the shear contribution from A, C, D, B. All right? Which is why you end up with 600 newtons and 300 newtons for the main beam, and then you've got a 3,200 Newton force for this little DF component. Now, because I set the reference fiber on the right-hand side, this shear force ended up being 3,200 newtons of shear, but if I were to place the reference fiber on the opposite side, it would have been positive. So again, it's all a matter of perspective as to what you're really trying to deal with. All right? For the axial force diagram, if you were to cut a section anywhere between A, C, and D, your axial force, if you were to draw it out in tension, would have to balance out this AX here, which would indicate that ACD is entirely in compression with a magnitude of 3,200 newtons. All right? Now the cable, obviously, that's kind of a known quantity. You don't really need to have the shear diagram or axial diagram for that. It's kind of pointless since you already know that the cable is tensed to 3,200 newtons, and it shouldn't have any direct impact on the stresses A, C, D, and B, because again, it's kind of like a separate structure almost. All right? Now the moment diagram, this is where things get a little interesting. All right? When it comes to the moment diagram, all right, we can use the moment area method, the shear area method. So we could find the bending moment at point C by taking that area. So 600 times 0.2 meters would give us 120 Newton meters. So I am gonna just draw draw this out as such. So that gives us 120 Newton meters. I'm actually going to draw it on the opposite side just because it's going to, you'll see where I'm getting at in a second why I'm doing this. So this gives us 120 Newton meters. From there, take 300 newtons and multiply it by 0.2 millimeters because this section here is technically going to be an applied moment, all right? So if you were to try and remove this, you would need to apply an equivalent applied moment here in order to contribute for the bending moment that's caused by that. So you take the area now of this area here and add it to the existing bending moment, which should give you 180. All right. But now, guess what? When it comes to bending moments, moments are a type of rotational force, which means you should account for the shear diagram here. All right? So that 180 Newton meters is then going to have to be subtracted by 3,200. All right, so we get negative 3,200 times 0.075 meters, which gives us a bending moment. If we were to draw out this diagram, this would be like that with a peak here of negative 240, which means when you add this, is actually going to bring this to about this point here. So at this location, there's actually 0 moment, but then there's a peak here of around 180 minus 240, negative 60. Which then, guess what? When you add 300 times 0.2, cancels out to 0. So, closes out.
That's negative 240, right?
Yes. So, if I were to ask you guys, what would the thickness of this have to be, and you guys were trying to size out the dimensions for, remember, FD, then you would need to consider a bending moment of 240 Newton meters. Whereas for this ACDB, the maximum bending moment is only 180. So, but you can see here that this would be considered as an applied moment, which is why it gets added directly to this. This is also one of the reasons why I didn't give you guys a frame on the exam, because once you start getting into weird junctions like this, it can be very difficult to really keep track of everything. Make sense?
How do you know how far out you put the negative 40? Is that supposed to represent this?
I didn't draw it to scale.
What is that supposed to represent?
That's the maximum bending moment at, basically it's, all of these points are basically assumed to act along the center lines of all the points. So really you're supposed to consider them as kind of like, it's supposed to be like the thickness is small enough to where it's not like, it's negligible. Because otherwise, if you were really looking at the nitty-gritty of it, you would kind of need the software to analyze the stress concentrations at those corners, because then the bending moments would really kind of vary. Have a good one.
So that length is the width of...
It's the full 75 millimeter length.
Oh, okay.
Yeah, so it's just the center line of all of the members. You basically just assume that it's line. We call them frame elements. So it's just two-dimensional line elements, if that makes sense. It's just a very gross approximation, just used for simplified design purposes. So, yeah, if you guys were to look at 2D finite element models and start going into like playing around with like SAP 2000 or whatever, you would notice that all of the analysis that's done is using like little lines, and then just estimating with that. It's not really like you're actually considering the full thickness and then the geometric constraints, because it just adds an entirely new level of complexity to the problem, Yeah. So you may see it for some instances where, if you have to go really into detail on like a small element, like for example, modeling like a connection detail that you're looking at, then you may want to have all of the nitty-gritty dimensions to really validate the stresses at particular locations and model the stress concentrations. But for this case, it's simple enough just for a global scale to figure out what thickness the entire assembly roughly needs to be. Make sense?
If a problem, like let's say this one specifically asks for the shear moment, would I have to include axial?
Not generally, no. But if, for example, the problem asked you, like, what is the stress at the top of the member at point C, it would help to have the axial force diagram drawn, because then you can use the combined stress equations that we covered in chapter 4. Otherwise, you may just accidentally overlook the axial force component, which is actually a significant part in this problem since it's 3,200 newtons of force. Yeah, Ryan.
For the axial loading, why do we not consider AX as a...
We do.
Oh, that is the...
That's for...
3,200 is AX?
Yeah, that 3,200 is basically from the AX. So
Okay.
you would need to... What we're not considering is the cable, because it's kind of like separate. So if you were to cut equilibrium right here and you were to draw the axial force and determine N, you would find that N is negative 3,200, which is where you get this negative diagram from. Any other questions? No? All right. Let's do another problem, unless you guys are getting sick of me. All right, so for this problem, the bending member in figure 14.18 is built up of 3 steel plates welded together to act as a single unit, generally called a plate girder. It's very common in like bridges. It's subjected to a vertical loading of 300 kips. We're asked to calculate the maximum stress in the plane of the neutral axis, and then calculate the shear stress at the junction of the flange and the web. And then it asks to plot the distribution of the shear stress for the entire cross section, which I think I'm just gonna skip that. I don't know yet. I guess we'll see. But I think ending 7 o'clock should be fine, because I think we all kind of want to go home. But yeah, if you guys have a good one. All right, so we'll give this problem the last one. So I'll actually cut that one, but it is in your textbook. So this one is not in your textbook, which is why I'm going over it. All right, so for this one, we first need to know the neutral axis. They actually give us where the neutral axis is located and where the centroid of the flanges are, which is nice and convenient. So to first find the maximum stress at the neutral axis, we first need to know, for part A, Q and Y bar, which is equal to A tilde times Y tilde. Now, A tilde is the total area of the flange and the web above or below the neutral axis. All right. So that A tilde is just going to equal let's see. So we could break it up into 2 components. We've got 1 and then 2. So we've got the flange and web. So let's see. I'll actually make a table. Part, flange, web, A tilde, Y tilde, and then Q is just the multiplication of the 2. So for the flange, the A tilde is just going to be 1.5 times 16, which gives us 24. the location of the flange from the neutral axis given to us is 24.75. For the web, it is going to be 48 divided by 2 is, again, 24 times 0.5, so that's going to be 12. And then y tilde is just going to be 48 divided by 4, which is just 12. So do some multiplication. This becomes 594, 144, which means that the total Q is just equal to 738 inches cubed. Now the I is also what we need. We would use the parallel axis theorem. This is just going to end up being 2 times 16 times 1.5 times 24.75 squared. That's the flange plus 16 times 1.5 cubed over 12. And that's just for the flanges. Let me actually, that 2 should be on the outside. Plus 48 plus 1/2 times 48 cubed over 12. And that should be the total IX. So this gives us 34,020 inches to the 4th. Is that what everyone's doing it? All right. Now we know that the thickness of at the point of interest, which is our neutral axis, is just 1/2 inch. So that B is just going to equal 0.5 inches. And then shear force is just 300 kips. So tau at the neutral axis is going to equal 300 times 738 divided by 34,020 times 0.5. And that gives us a stress of around 13.02 KSI. All right, and a good kind of check that I just did, I just ran the average web shear approach. So that's just taking the area of the web and then doing 300 kips divided by the area of the web, which was 48 times 1/2 inch is just 24 inches squared. And that gave us around 12.5 kips per square inch. So we know that this shear stress has to be relatively correct. All right, otherwise if we were way off, we know that we did something wrong. All right, so that's the stress at the neutral axis. What about the stress at the junction of the flange and the web? So let me copy paste this to another slide. And then let me just erase all of this in red. And then I'll do it in like blue or something. So at the junction of the flange and the web, it's basically just analyzing it at that location there. Excuse me. So this is part B. So part, it's just going to simply be the flange this time. There's no web. We're going to have an A tilde, Y tilde, and then a Q. So our A tilde then becomes the 16 times 1.5, which is again just 24. Y tilde is going to be the 24.75. So our Q just becomes 594. Now excluding anything from the web. All right. Now, what we're going to have is two values of B. We're going to have a B1 and a B2. B1 is going to be the width of the flange, which is 16 inches. And then B2 is going to be the thickness of the web, which is 0.5 inches. The reason for that is because at the junction, there is an immediate jump from when we go from the web to the flange, which is where we get that weird kind of jump in the profile. All right. I is just for the entire cross section, which we had previously calculated as 34,020 inches to the fourth. And so tau at, I'll call it E, because that's the location of the junction, is equal to the 300 kips times 594 inches to the fourth divided by 34,020 inches to the fourth. And then just to kind of signify whether it's the shear stress for 1 or 2, I'll do one circle here, multiply it by 16 inches. Which gives us a shear stress of around 0.33 KSI in the flange. And then tau E2 would just be the same thing, but instead of using 16, use half an inch, which should give us 10.48 KSI. All right. And then the last part of this problem is just what would the stress distribution basically look like? We can kind of rough hand it since we don't know the exact values. So if I take this and I draw a little diagram just along the height, we know that the shear stress is 0 at the top and bottom, so the very edges of the beam. So it starts out 0 and 0. We know going down 1.5 inches, it maxes out to about 0.33 KSI for both. And then from there, there's an immediate jump to around 10.48. So that is around 0.33. 0.33. This becomes 10.48. 10.48. And then the shear stress distribution is always quadratic in nature. Where the maximum shear stress just becomes 13.02. And this is the shear stress at the neutral axis. Any questions about this? How you guys feeling about the exam? All right. Well, I'm sure you guys will do fine. Just prepare that formula sheet and try and get familiar with it. Maybe try doing some problems with just the formula sheet. And then, yeah. Any other questions? Brian?
For shear stress about the neutral axis, for some shapes, it's not like how mass isn't at the neutral axis. Is that when there's not like a line of symmetry?
Yeah.
Okay.
Yeah, because you'll notice for the triangle problem on the latest homework, yeah, it's y over 6 above. It's, I think, height over 6 above. So it's slightly skewed wherever the maximum shear stress is. Yeah, so
Axis is height over 2.
so it's wherever really the for asymmetric shapes, the maximum shear stress isn't always at the neutral axis. In most instances, it will be. In the cases where it's asymmetric, it will generally be very close to it. Yeah, so, but fortunately, most materials in nature are generally symmetric, just because they're easy to design with and generally easy to manufacture if they're symmetric. So because of that, it shouldn't be too much of a concern most times. Plus, you're never seeing steel shapes in the shape of a triangle.
If they're not symmetric, is the only way to do it to take the derivative of it?
Yeah, you would need to take the derivative and validate what the slope is using the inflection point.
That might be like a cheap way to do it.
Nope.
Okay.
No cheating. No cheating in life, unfortunately.
Okay.
All right. I'll upload